Hello friends, this is mechanical vibration lecture, lecture series 5, part 2, which is all about the free vibration response of damped system. And under this, in this lecture, what we are going to cover is about, we already discussed about the viscous damping condition and then various conditions in viscous damping, and then we try to recap all about the Coulomb damping condition. So under Coulomb damping, what is the amount of energy dissipation during Coulomb damping? What is the amplitude decrement in every cycle? How the energy dissipate, or how the energy and how the vibration will go and cease after some times. So we already discussed those in the previous lecture 5, part 1. So I'll add one example on that topic for Coulomb damping, and then we directly go to the next topic that is called hysteretic or structural damping. What is hysteretic damping in the mechanical system? What is how we can analyze this part? So let's see this part. Okay, so let's continue. So we already discussed about free vibration response of systems Coulomb damping. So we are going to see the structural or hysteretic damping. Before going to structural damping, let's finalize the Coulomb damping condition. In order to analyze Coulomb damping condition, we must use some examples which can easily give us the highlight of the condition. So let's see. The equation of motion for damped vibration with the highly nonlinear, because this Coulomb damping is highly nonlinear damping condition. So how we can express the equation of motion of such highly nonlinear kind? For example, let's take this x dot dot plus zeta x dot plus x plus cx to the power of n, which is equal to 0. So this term indicates the equation of this equation is second order differential equation, but it is not linear equation. In order to be linear, this term should be 0, but here it is not 0, it is cx to the power of n term. Okay, so in actual case, as we know, x dot dot plus x dot plus x is equal to 0 is the linear case. So this non-linear part with n is equals to 2p plus 1, for which p is equal to 0, 1, 2, 3. So if p is 0, then we can get constant that is also still non-linear, but so where the superposed dots denotes the differentiation with respect to that is already known, and zeta is the damping coefficient, and c is the constant parameter. Okay, and n is the degree of non-linearity. Okay, this n indicates that the degree of non-linearity. Okay, so the initial condition in this case, as we have seen in the previous example for Coulomb damping case, x of 0 is equal to 1 and x dot of 0 is equal to 0. So this is almost similar to the previous example. Can you go back and see the previous example? Let's see the example. Look, in this example, initial condition x of 0 is equal to 0.5 meter, x naught is equal to 0, and other parameters like mass, stiffness, and friction coefficient are given. And we apply this rank method. Okay, so similar approach, we can proceed with this highly nonlinear equation. Okay, so these are the initial conditions. This is the equation of motion. So let me highlight. Okay, okay, where is the pen? The show previous screen. Okay, let me take the pointer. So this is the equation of motion considered, and it is highly nonlinear. Okay, let transformation domain for this, let y of t is equal to x dot of t. Like what we have done there, x2 is equal to x1 dot. Okay, the same principle. So y dot of t is equal to x dot of t. Like we have done, x2 dot is equal to x dot t. So this is the transformation domain. And then applying this equation to the previous equation, what you can get is, this is the equation. Y dot plus zeta y plus x plus cx the power of n, which is equal to 0. Okay. Now the initial conditions become x of 0 is equals to 1 and y of 0 is equal to 1. That is the given initial conditions, which is this one. Okay. So by a process of inverse differential transformation, the solution of each domain taken n plus 1 terms of the power series will be like xi of t is equals to the summation of t over this theta is the variable t, which we consider, of I from k is equal to 0 to m, xi of k for 0 to 0 is less than or equal to t less than or equal to zeta I. So where I is equal to 0, 1, 2, 3 to n, indicating this I is subdomain. K is 0, 1 to m denotes the term of power series, and zeta I represents the subdomain interval, and x of ik and y of ik are the transformed function of x of t and y of t respectively. So from the initial condition, x naught of t is equals to delta of k, where delta of k is a chronicle delta actually, which is equals to 1 actually. 0k is equal to 0, 1k is equals to 1. This is 1, not blank. And the y of naught is equal to 0. Why? Because y is equals to x dot. X dot in the initial condition given, x dot of t is equal to 0 is 0. That means y of 0 is 0. Okay, so these are the initial condition. And this delta is the chronicle delta function. From equation 1 and 2, we have here equation 1 and 2. This is equation 1, this is equation 2. You can represent 1 and 2. We have these equations. Equation 1 and 2 are these equations. We can represent these equations 3 and 4. 3 and 4. Okay, from equation 1 and 2, under differential transformation, which yields k plus 1 over zeta I, xi of k plus 1, which is equal to yi of k. Okay, this is like this, not bigger bracket. This is not applicable. Sorry. Then k plus 1 over zeta I, yi of k plus 1 plus zeta yi k plus xik of k plus c summation of n plus 1 over k l minus 1 for l is equal to 1 to k times xi of l over xi of 0 times xi the power of n times k minus l is equal to 0. This is the power series expansion for the a given function. So the present derivation employs the DTM described above to generate a number of numerical results for the response of damped system with high nonlinearity. Therefore, this damped system with high nonlinearity is the best example for the Coulomb damping condition. The response of x of t for different values of nonlinearity n and different coefficients zeta, these are plotted in the figure in the next page. Look, this is using the rank-Kuta method, numerical solution for nonlinear case. Look, this is x versus t plot. Okay, x versus t plot for different rank-Kuta solutions and differential transformation solutions. Straight line indicates differential transformation solution, and the dotted lines indicates rank-Kuta solutions. They are almost coincident for different zeta function. For example, zeta is equal to 0.02, very small value of damping coefficient, 0.2, and 1. 1 means critically damped condition. Again, here we can see x versus t plot for various value of as increasing of the zeta function. Okay, this is also another solution. Figure A, comparison of differential transformation method and rank-Kuta numerical method. A for n is equal to 3 case, B is n is equal to 100. Yeah, one thing that we must understand is this is A means n is equals to 3. B case means, sorry, not B that, n is equals to 100, 1. And C is equals to, n is equals to 1001. 1001. So this is a float of xt float for various value of zeta for damping ratio and for different value of n. Okay. As n is very small, these things we can easily identify, they are scattered. But in the case of n is very high number, then we can observe them, they are very merging together. So it is noted that the present results are an excellent agreement with the numerical result obtained from the fourth order rank-Kuta approach. This figure presents the displacement of velocity time response of damped system with nonlinearity of the order of n3, n101, and n1001. Okay. So the result in case the amplitude decay are more rapidly for higher value of nonlinearity, particularly at higher value of damping coefficient. So here we can see the displacement time plot. Okay, this is time axis, this is displacement axis. You see, this is zeta 0.2, zeta 0.02, zeta is equals to 1 case. So in the case of 0.02, we can see this light line having high amplitude. This is for the logarithmic decrement or the decrement of amplitude for zeta is equals to 0.02. This is very what we call this as underdamped vibration case. Again, another underdamped vibration case, we can observe the amplitude like this, this. So we can observe similar thing here. This is for zeta 0.02. Okay, and there is also another case, and that is zeta is equal to 1. Zeta is equal to 1 case. We can see some float here, which start from here and stopped here. This is all. So that is the difference between the two. Here also for velocity time response, we can see x dot, okay, x dot t case. Similar graphs are there. Okay, this is for very small amplitude and very small zeta value 0.02. Another one is this for 0.2, and another one is simply like this over here. This is for zeta is equals to 1 case. Okay, now let's go to the next topic that is called structural damping, or what you call it as hysteretic damping. So in this topic, we also make a comparison between Coulomb damping and structural damping. So the damping caused by the friction between internal planes that slips or slide as the object deform is known as hysteretic damping. So this is an internal friction. It is not a friction which has the surface, but it is in the planes of the surface of the crystals. So we can take crystals in this case. Okay. So in the structural damping caused by contact or impact at joints. In the case of this structural damping, we consider it is caused by contact or impact at the joints. Energy dissipated is determined by means of coefficient of restitutions of the two components that are in contact. This forms the damping is caused by Coulomb friction at structural joint. It depends on many factors such as joint forces or surface properties. The area enclosed, for example, this is loading and unloading cycle in the case of structural hysteretic damping case. Okay, this is the loading cycle, and then it comes down, and this is from here to here. It is unloading cycle, the bottom line indicates unloading cycle, and this is the loading cycle. So there is area which is covered inside of these two paths of the hysteretic loops. So the loading and unloading forms a loop known as hysteretic loop. And the area inside of this is known as the amount of energy dissipated per unit volume of damping. Okay? So it is the area of hysteretic loop is energy dissipation per cycle. Okay, that is energy dissipation per cycle, and the term does per unit volume damping capacity, D. Okay, so D is equal to delta W, then delta W is equals to pi omega Cx square. It seems the same as the previous Coulomb damping case, but we'll see it, how it is different from the previous condition. Not Coulomb, but viscous damping case. The viscous damping, the amount of energy dissipated is equal to pi omega d Cx square. But here it is pi omega Cx square, not omega d. Anyways, we'll visualize all of them. The purpose of structural damping is to dissipate vibration energy in a structure, thereby reducing the amount of radiated and transmitted sounds. Okay, that is the purpose. Anyways, here we can observe stress strain curve. This is a stress strain plot. So free vibration is hysteresis damping. So let's consider actually this is a spring damper system of vibration in a spring damper system. Okay, so consider a spring damper, viscous damper system arrangement as shown in the figure. F needed to cause displacement x of t is given by F is equal to kx plus cx. In this case, F is equal to kx plus cx. For harmonically excitation, omega and amplitude x, so x of t is equal to x sine omega t. Actually, here we are going to identify what is this length and what is this length. Previously, I promised to see these things, so let us see how we can find these values. What is this value? How we can calculate? How is this obtained? So now, considering these two equations, because x of t is equal to x sine omega t is a harmonic solution, therefore x dot of t is equal to omega x cos omega t. So let's substitute this into the equation. What will be? So F is equal to kx sine omega t plus Cw x cos omega t. So x cos omega t means we are making some rearrangement, some smaller rearrangement here. X cos omega t is the whole square and radical. Now this means x square cos square omega t, because I'm going to make some arrangement on this equation. For that, let's do this. As we know from the trigonometric identities, we have cos square omega t is equal to 1 minus sine omega t. So let's substitute this term in the place of this cos omega t. So finally, k x sine omega t is this term. Cw x square 1 minus sine omega t sine square omega t. We substituted instead of cos omega square this term. Then it becomes 1 minus sine omega square sine square omega t. Now look, this is still the same. Cw is Cw, so x square minus x sine omega t is the whole square. X sine omega t means in the solution given, it is x of t. So x of t is equal to x sine omega t. So let's substitute this into x sine omega t. So x square minus x of t square by substituting this term. So this is the equation of force. And here kx sine omega t. So x sine omega t is x of t. Yeah, here it is x of t. So when so from here we can simply observe kx term is this term. This is kx, and then this is Cw x square x square. Cw capital X square. This is amplitude of vibration. That is magnitude of amplitude of vibration, and x of t is the sinusoidal function. So this is Cw radical of x square minus x square. So the derivation is directly from this concept. So when f versus x is plotted in equation 3, represents a closed loop path. This is a closed loop. Okay? Equation number 3 means this equation. Where is equation number 3? Yeah, equation number 3 means this equation. In this equation, we can plot this type of graph for minus of x to x, the amplitude, and from CWX to minus CWX. Okay, CWX to minus CWX in the y plot. Okay, x the cosine plot, and in the sine or in the x plot we can find k, this x x to minus x. So these are the terms which we can easily identify. And the area of the loop denotes the energy dissipated by the damper in cycle of motion, and is given by delta W, which is pi omega Cx squared. This is pi omega Cx squared. So now in the case of hysteretic damping, the energy loss in loading and unloading cycle is equal to area closed by the hysteretic loop. So this is the hysteretic condition. Okay, hysteretical damped condition. This is viscous damped condition. So it was found experimentally that the energy loss per cycle due to internal friction is independent of the frequency, but approximately proportional to the square of amplitude. Still, it depends on the square of amplitude. In order to achieve this observation here, the damping coefficient C is assumed to be inversely proportional to the frequency. C is equal to H over W. Here H is the hysteretic damping. C is the viscous damping constant, and H over W is the hysteretic. Means here C is inversely proportional to damping coefficient. C is inversely proportional to omega. This implies the proportionality constant here is the hysteretic damping constant H. So C is equals to H over omega. H over omega. So let's substitute C is equal to H over omega in the delta W equation. Then finally what we can get is pi Hx is the amount of energy dissipated in every cycle of hysteretically damped structure. Now, let's consider the complex stiffness condition in the case of hysteretically damped system. In our figure A, we have here figure A and figure B are there. So the spring and okay, this is actually this case. Figure 1, A. Spring and damper are connected in parallel, and for a general harmonic, x of t is equal to x e I omega t. Therefore, f is equal to kx e is a power. This is the solution type also, using the exponential function. Not only we can use trigonometric function, or we can use exponential functions. So kx e I omega t plus cwi x e I omega t. This is a complex form of system. So which is equal to k plus ic omega the whole x of t. Similarly, the spring and hysteresis damper are connected in parallel as shown in the figure. This is for spring and hysteresis. Here, the spring, the damper is represented as H. This H is equal to C omega. Here it is C. Okay, so this is for hysteretic case. This is for spring dashboard system. So in this case, we directly substitute instead of C, H over omega, so that it gives K plus F is equal to K plus IH, because here it is K plus IC omega X of t. So instead of K plus IC omega, so instead of C, we substitute H over omega. Then this cancel each other. Finally, what we can get, K plus IH of X of t, which is equal to 1 plus IH over K. Just multiplying with K outside. So this H over K is known as the complex stiffness of the system. Okay, that which is dimensionless measuring of the damping, which is represented as beta. Okay, K plus I beta. Okay. Now K plus 1 plus I beta is the equation. So K plus I beta is called the complex stiffness of the system. And the B, which is equal to H over K, is a constant indicating dimensionless measure of the damping. So this, in terms of beta is equal to H over K, the energy loss per cycle can be expressed as delta W is equal to pi H x squared. So instead of H, we can represent H is equals to beta times K. Then we substitute it. This is pi K beta x squared is the amount of energy lost per cycle. Under hysteretic damping, the motion can be considered to be linearly harmonic. Therefore, delta W is small, and the decrease in amplitude per cycle can be determined using energy balance. Okay. In order to determine the amount of energy decrease in amplitude of the motion, we must consider the energy balance. So for that, let's take some points. For example, this is the type of motion expected. And then let's consider some point P here, and the point Q here, okay, point P, and point Q, point R, 3 points. So initially, let's consider this amplitude as xj. And then after half cycle, we can get this as xj plus 0.5. That is half cycle. And after full cycle, we can get amplitude xj plus 1, still decreasing amplitude. So we can evaluate it for every half cycle. So separate by half cycle. So for given half cycle, xj square over 2 minus pi kb xj square over 4 minus pi kb not beta xj square for 0. J plus 0.5 over 4, which is equal to kxj square kxj plus 0.5 over 2. That gives us xj over xj plus 0.5, which is equals to radical of 2 pi plus 2 plus pi beta over 2 minus pi beta. The energy at point Q and R are given by at point P is xj. Okay, and at point R is xj plus 1. So it is Q and R actually. Q and R is xj plus 0.5 and xj plus 1. Okay. So Sj plus 0.5 over Sj plus 1, which is equal to 2 plus. It continues like this for every half cycle. The amplitude ratios are continue like that for every cycle. Therefore, for the 3 points, which are from point P to R, sorry for sneezing. So for full cycle from point P to point R, that is full cycle, okay. What will be? Xj over Xj plus 1, which is equals to, we can multiply the two terms. Which term? This one and this one, because it is the continuation one from another. So by multiplying the two, we can get this term, and that is finally 1 plus pi beta. This is constant because beta is the constant dimensionless. Pi is pi 1, so it is constant. The hysteretic logarithmic decrement can be expressed delta is equal to ln of this xg over x. So that finally gives us ln of 1 plus pi beta, which is equal to pi beta. So that is the logarithmic decrement. Since the motion is described to be approximately harmonic, the corresponding frequency is defined, omega is equal to q over m. The equivalent viscous damping ratio can be found by equating the relation for the logarithmic decrement delta. So delta is equal to pi beta here, which is equal to pi h over k, which is approximately equal to 2 pi zeta equivalent. So we can find the equivalent damping ratio zeta, which is equal to h over 2k, or which is equal to beta over 2. And C equivalent, that is the equivalent damping constant, which is equal to C critical times zeta equivalent. So, which is Bk over W, which is H over W. These are the relations. The question of hysteretic damping. Let's take one example, which can clearly gives the full idea what we have discussed. So the experimental measurement on structure graph, the force deflection data shown in the figure. This is the force deflection data. This is force axis. This is deflection axis. So 0 to 500. Okay, minus 500 to 500, and minus 10 to 10 is plotted here. We can see the loading and unloading cycle of hysteretic loop here. So for this data, estimate the hysteretic damping constant at the logarithmic decrement. So we have given only this table or this chart. And based on this chart, we can make or we can calculate various parameters in the hysteretic damping condition. What you can do? So this is the energy dissipated, and each full load cycle is given by the area enclosed by the hysteretic curve. So the full area under this curve gives us the amount of energy dissipated. Now, based on the scales given here, we can divide this section into three important sections. Rectangular section, and there we consider simply a triangular section, even though it is not exactly not triangle. Let's consider this length as 1.8, this length as 8 by counting this with respect to our cubes here, not cube but rectangle. And then calculating the area inside of this, finally we can get the amount of energy dissipated. Okay, so the total deflection x is equal to 8 millimeter. Force is from 400 to minus 400 to 400. Okay, so how we can calculate? Let's see. Each square in figure represents the area of individual cross section, which is 2 millimeter by 100, which is 2000 Newton meter. Okay, so we can see each area here. For example, area of this, if I take area of this cross section is equals to height 100, and from here to here 2, so 100 by 2, it gives us 200 Newton meter, Newton millimeter, because this is given in millimeter. Okay, Newton millimeter. Okay, the area enclosed by the loop can be found as summing all the areas. Total area is equal to delta W, which is equal to area of ABC, plus area of ABDE, okay, area of ABDE plus area of DEF or EFD, okay, area of DEF, which is equals to, we consider that the two areas in the margin as a kind of triangle, that is approximation, which is equal to half AB plus CG. And the inner part as rectangle, so AB times AE plus half DEFH. So what you can get, the cross sections, every dimensions are there. Okay. From here to here, consider 1.25. This is considered 1.8. From here to here, it is 8. So substituting this, finally we can get 12.25 square units. So delta W is equal to pi hx squared, which is 12.25 times, this is just for a single, so for the overall, we multiply it by 2000 Newton millimeter. So 24, 2000 means this one. So 24, 2450 Newton millimeter or 2.45 Newton meter. The maximum deflection x is 0.08. From where we can get this? We can get the maximum deflection here. From here to here, 0.08, or it can be from here to here. So it is approximated or taken 0.008 meter or 0.8 millimeter. And the slope of the force deflection curve is equal to k is equal to 400 over 8. Means how we can get force from here to here, it is 400. Means slope k is the slope of the graph, delta y over delta x. So which is equals to delta y from here to here 400. Okay. And the delta x is 8 millimeter. From here to here it is 8 millimeter. 8. So that gives us the slope. That is 500 Newton per millimeter or 5000 Newton. Newton per meter. This is 50 Newton per millimeter or 50,000 Newton per meter, not per millimeter. 1 millimeter is 1 over 1000 meters, so that it is like this. The hysteretic damping constant H is equal to delta W over pi x squared, because we have delta W is equals to pi h x squared. From that relation, we have this. So the hysteretic damping constant H is equals to 12,185.4 Newton per meter. And the loss factor of hysteretic damping, that is called beta. So H over K. Immediately substituting this value, we can get the loss factor. And the logarithmic movement delta is equal to pi over beta. So once we get the loss factor, then we multiply it by beta, then this is the delta value. It is in millimeter, I think. Delta, yeah, it is logarithmic decrement actually. Note that the method of finding an equivalent viscous damping coefficient for structural damped system is valid only for the harmonic excitation. So the above analysis assumes that the system responds approximately harmonically at the frequency omega. So this is the complex stiffness which we have discussed. Everything is there. Okay. Beta h over k, k times 1 plus I beta is called complex stiffness. Delta w pi k beta x square, or which is equals to pi h x squared. This is what we have discussed. And in the case of forced vibration, we'll see this part in the forced vibration case, not now, but simply just to consider assuming f of t, which is f naught cos omega t, as an excitation force. Okay, during that time, what will be the equation? Previously, what we have discussed is with no force, but here assuming the forced vibration with hysteretic damping. So the equation becomes like this, and we have particular solution. X particular of t is equal to x cos omega t minus pi. Pi is the cos difference, x is the amplitude, and then the amplitude x is equal to, can be this equation, f naught over radical of k squared 1 minus omega square over omega n plus beta square, and tan pi is equals to beta over this quantity, 1 minus omega square omega n square. So this is the hysteretic damped condition with some excitation force f of t. And the amplitude ratio x over f naught over k reaches its maximum. That for beta is equal to 0, beta 0.2, beta 0.5, beta 0.1, and so on. How it decreases? This indicates that as we increase the beta value, how this amplitude ratio decrease. Okay, and the phase angle omega over omega n versus pi versus omega over omega n. How it behaves? This graph shows the phase pi has a value in the case of hysteretic damping. This indicates the response that can never be in phase with forcing function in the case of hysteretic damping. And the hysteretic damping ratio can be R is equal to omega over omega n is equal to 1. That is the condition here. Okay. So depending on initial and elastic conditions, that hysteretic loop method, based on the inertial and elastic constant, the loop will change, but the work done in the conservation force will be 0. Consequently, work done will be equal to energy dissipated by damping only, without normalizing the respect to mass. The energy dissipation per hysteretic loop of hysteretic damping is delta U V is equals to pi x naught square omega c. And the initial maximum potential energy is pi x naught omega h. And the loss factor be h over k of 2 over zeta. And zeta is equal to h over 2k. These are the relations. And what are the methods applied for the hysteretic damping? There is a Maxwell method. So in the case of Maxwell method, we can observe C and K are in series. C and K are connected in series. There is a Kelvin-Biot method or model. Many scientists model in different ways. So how the Kelvin-Biot model did? This model, the K and C are connected in parallel. And then when we come to standard linear solid mechanics, solid model, the standard linear solid model, we call it the Zener model, which models K1 and K2 in parallel and K2 with C in series. So combination of series parallel combination. So these are some of the models of hysteretic damping. So thank you very much for your patience. This is all about undamped free vibration case and the what you call this various type of damping conditions. And then the next we directly go to the forced vibration case. The forced vibration, that also is one of the main topic of our lesson. Again, thank you very much. This is all about today.